I'm Hemant Mehta.
And I'm Jessica Blimke.
And you're listening to the podcast for FriendlyAtheist.com. You can now listen to all of our episodes and see show notes at FriendlyAtheistPodcast.com.
By the way, we now have a merchandise shop on the website. So if you want your podcast swag, and you know you do, go to our website and click on the store tab.
Keith Devlin is a mathematician who is also known as the Math Guy on NPR's Weekend Edition. He's written several books explaining math to the masses, and he's the co-founder and executive director of Stanford University's Human Sciences and Technologies Advanced Research Institute, better known as H-STAR. Keith, thank you for joining us. And can you explain to us what H-STAR actually is?
Besides what should be your rap name.
To be with you.
Besides your rap name, which it should
No,
be.
your rap name.
My rap name, too, yes.
It's one of these classic academic titles. The letters H-STAR stand for Human Sciences and Technologies Advanced Research. And it's an institute, a multidisciplinary institute that does research and that's suggested by the name. It's research that involves the human sciences, but also with technology. So we basically fund research and we support research at Stanford. It's all Stanford internal research, although we do collaborate with universities and governments all around the world. But we deal with research that intrinsically involves both the human sciences and the natural sciences, engineering, and technology.
So I have a pretty basic question for you. I mean, I majored in math. I taught math for several years. I'm pretty decent in math. And yet when I've seen math research papers or anything like that, I am so lost. Why is math so hard? I mean, I'm not bad at math, but I'm totally lost when it comes to advanced stuff. And I know I've taught so many students who have trouble grasping what I now consider the basic stuff. What is it about math that makes it so hard for some people?
It actually changed quite dramatically about the middle of, starting in the early 19th century, but predominantly during the 19th century, it changed into an extremely abstract discipline. It went off in many different sub-directions, each one getting increasingly abstract, certainly built on the basic ideas. But those basic ideas of sort of algebra and arithmetic and geometry and trigonometry and so forth, and then calculus from the 17th century. Those in some sense had been worked out, they'd been well worked out, they were full of applications, but each of those and various other disciplines in mathematics led to sub-disciplines, and those sub-disciplines led to sub-disciplines, and as mathematicians went out on these various tracks, these different paths, and bifurcated their interests, it got more and more abstract, the notations got more abstract. So that today, someone like me, who's been a professional mathematician all my life, I got my PhD by going down one track and going down a long way till I got to the frontiers. But by that stage, when I'd got a PhD and people regarded me as a professional mathematician, which indeed I was making money doing it, I could no longer understand the mathematics done by my colleagues down the corridor because they'd gone down a different path. So the way you feel about it, Herman, and most people feel about it, I feel about other branches of mathematics. When Andrew Wiles solved Fermat's last theorem in 1994, because I know him vaguely, I know him a little bit better now, I was able to I actually got a signed copy of his paper, which is one of my treasured possessions. Absolutely awesome. But I opened it, and I couldn't get beyond about 3 or 4 sentences down the first page. It was clear that as a professional, if I was willing to devote maybe a year of my life to learning that branch of mathematics, I could probably begin to understand it. But it was as alien to me as any branch of modern mathematics would be to a layperson. So it's the same in the field as it is to someone outside the field.
For someone like Andrew Wiles, who is known as this great mathematician who solved one of the great mathematical problems, I mean, it sounds like what made him so powerful and what makes him so powerful, he is grabbing math from so many different frontiers, to use your word, and bringing them together and finding connections no one else did. How is he able, I don't know if that's right or not, but how is he able to draw around, how is he able to figure these things out? That
it wasn't really many different fields. The thing that happened, and there was an element of luck in this one, was there were two fields of mathematics that for various reasons, accidents of advisors and who he'd been working with, there were two branches of mathematics, two distinct ones that were actually thought to be very different, that he knew very well. it turned out that the solution to Fermat's last theorem required the marriage of those two branches of mathematics. So he was almost unique in being a master of the very two areas of mathematics that needed to be brought together. That's happened in other disciplines, other proofs as well in mathematics. Very often what's happening these days is when a problem has resisted solution for many years, it turns out that no single discipline is enough to solve it. You need to marry two disciplines. And the mathematicians who have done this have been mathematicians who've known those two disciplines. I'm not sure if there are many or any mathematicians who are masters of three different branches of mathematics. And it may well be that some of the unsolved problems of mathematics may require mastery of three branches of mathematics, and we may not ever have such a mathematician today. Now, we used to many years ago. I mean, Euler, back in the 1700s, was renowned for being a master of many of what were then the leading branches of mathematics. But today, you cannot be another Euler. You can't master all of the branches. There are a few mathematicians who are masters of two of the branches. And as I say, I don't know if there's anyone that's mastered three. So we may have maxed out on the kind of theorems we can prove now.
So the idea you kind of spoke about how the paths of math have gotten further and more complicated. Does that mean somebody who's, say, in high school today who wants to major in math is going to have a harder time getting to that frontier because there's so much more path to go?
Well, it depends on which branch of mathematics you choose. First of all, there's new branches of mathematics opening up all the time. So when I was a graduate student in the late 1960s, early 70s, I went into a branch of mathematics which had only been opened up 4 or 5 years earlier. And so there was still plenty of results to do. It only took me maybe 6 months to get to the frontiers of that discipline. And that's still the case today, so that the smart people who really want to sort of make a career will choose new mathematicians. There are many cases, by the way, of very smart people becoming graduate students. They talk to their potential advisor and they say, I want to work in number theory because it's been going for hundreds of years. And the advisor will say, well, you can if you want, but if you want to get a PhD in 4 or 5 years, you'd better put that to one side. Work on something else, get your PhD, and then if you still want to do number theory, say, move back into number theory. And so you have to negotiate your way through this field. But mathematics is constantly growing, and if you're in a new area of mathematics, then the frontier is only maybe 6 months away.
Okay, I'm really sorry to be dense, and I hope I'm speaking for some of the listeners because I'm sitting across from a math teacher. I'm talking to a mathematician. I was a literature major with an incomplete dance minor, so I hope I'm speaking for more people. When you say branches of math, what I don't know what that means. Can you give me examples of branches of math? And I'm so sorry to be so basic. I'm just trying to begin to access this conversation.
The ones that are familiar to most people are things like arithmetic, geometry, trigonometry, different parts of mathematics. Then, of course, there was calculus, probability theory. Today, there are things like sort of dynamical systems, which is related to fractals. There's branches of mathematics being developed in connection with biology. There's lots of branches of mathematics came out in connection with physics. But they're just these different subdisciplines that, in the case of a high school, would be maybe a topic. The teacher will say, this week we're going to study trigonometry.
Sure.
Next week we'll do a geometry. Those are branches of mathematics.
Okay. So what did you study?
As a graduate student, I studied, in the general term, I studied something which at the beginning of the 20th century would have been called logic, mathematical logic. But by the time I came into it, in the 1960s, logic had already split up into 6 or 7 subdisciplines, and I picked a discipline called set theory. And set theory had split up into several subdisciplines as well. I worked on something called axiomatic set theory, and within axiomatic set theory in 1963, a new subdiscipline sprung up called independence proofs. And I was within 5 years of the splitting up, so I got into this whole area known as independence proofs.
Are there math schisms between the independent,
like gangs?
Yes, like religious sects.
The Jets and the Sharks?
Not really, although when you're outside one of these things, the people down the corridor, if you walk into one of their seminar rooms and you listen to them, you might just as well have been going into some strange sect where they have these strange rituals and strange terminology. You don't even know what the words mean. Very often, they're using words that are familiar, but after 5 minutes, you realize that they use those words to mean something very different.
Yeah, I mean, I was totally on board when we were talking about, like, geometry. I know what that is. And then literally the next thing you said is like, I don't know, I'm done.
One of the things about these,
the
when you go down these pathways and stuff, the question I get from high school students all the time, of course, is when are we going to use this in life? And at least at the high school level, for most of the classes, I can answer that question in most classes.
Sure.
But when you're talking about going down these pathways, I mean, like you said, so much of this is abstract. Where is this just a matter of, this is just a fun intellectual exercise, or is this stuff applicable?
For those of us that do it, it's almost always the motivation is it's a fun intellectual exercise. In fact, when I went into mathematical logic, it was regarded as one of the least potentially applicable branches of mathematics of all time. I went to this thing called abstract set theory, which was dealing with infinite sets of strange higher order infinities. That was all thought to be completely irrelevant. Post 9/11, I found myself working for the CIA on trying to improve intelligence analysis. And why did they ask me to join? Because someone at the CIA had read my stuff. I think people at the CIA follow me all the time these days, actually, and the NSA even more so. But the CIA, someone had read some of my papers, and they said, what this guy's doing might be relevant to us as we try to improve intelligence analysis. So within a few weeks of 9/11, I was working on this big national project. It wasn't classified. I mean, I can talk about it without having to kill you afterwards. It was purely using the ideas. It wasn't using the specifics of infinite sets that I'd done my work on, but it was using the thought processes. And that's usually the case. This is really the answer you can give to the students. Almost any branch of mathematics, the actual problems you're working on are probably not the kind of problems that would crop up in real-world examples. But the kind of thinking you develop to work on those problems can and very often is extremely valuable in the real world. And in my case, it turned out that the kind of thinking I'd been doing to work on these problems of infinite abstract sets turned out to be just one of the things that was required to understand the complexities of trying to do intelligence analysis in a global world.
I got to say, of all the ways I've ever thought about dying, being killed by someone who's been on NPR has never crossed my mind.
I really feel like we kind of buried the lead, that we got to CIA 10 minutes into an interview. We need to make sure we put that in the show notes.
Sorry. We'll put that in the show notes, CIA.
I mean, I will.
They'll never come after us.
Hammond, to your...
listen to this program and then you'll have to be killed after.
Right.
Hammond, to your point, though, like, I got started in the current job I have. I'm a writer by trade, and then I kind of moved on, and I use algebra every day. And I wish I could go back to, like, 16-year-old Jessica and be like, dude, pay attention for, like, 5 minutes. Future Jess will love you.
Yeah. See, here's a question I have just about mathematics in general. There are mathematical developments, new papers being written all the time.
Yep.
And the same thing happens with science research papers as well. And one of the things that happens is if you open up, a good newspaper, a good website that is talking about these things, they will talk about the scientific advances. I'm not saying they always do it well, but they talk about the scientific advances all the time. This is what a new research paper shows. Psychology, this is what a new research paper shows.
Wine will make you live longer.
No one ever talks about mathematics. Is it just because it's so complicated to understand and explain?
What are the papers about? Like, I know that's a terrible question.
All of these different branches, people are coming up with new results all the time. They post their papers online, but you never hear about them. And is it just because there's 3 people in the world who understand what's going on anyway?
I think so.
The real problem is that we don't have these very simple visual metaphors that you have in the other side. For example, in physics, no one, not even physicists know what matter looks like and consists of. There's these, but they have these metaphors like, first of all, there's the atomic model, the classic model of the atom, the billiard ball model, or the planetary system, where you've got a nucleus and you've got these electrons floating around it. The atom doesn't look remotely like that. It doesn't look like anything. And yet that's a nice metaphor to have in mind.
Sure.
Or Brian Greene talks about string theory, and he talks about these little loops of vibrating strings. Well,
because string theory is so accessible.
But it's so. But you've got the metaphors, and so you've got these physical metaphors, and they actually prove quite useful. mathematics, the metaphors themselves are abstract. So you can't even talk about them in terms of the real world.
But can
you
you
can
talk
sort of
about...
somehow come close. I mean, the reason I got on I became the math guy is it turned out that through an accident of birth or the way I think, some of my metaphors actually can be sort of visualized. I once talked about gravitational pull by talking about rafting down a river, where you're rafting down a river and you come to the rapids and there's two rivers go off and you're in the middle of the rapids and then you're in an unstable equilibrium, which means a small push with the oars can send you either careering off to the left or careering off to the right. Now, I use that metaphor to talk about unstable equilibriums with sort of planetary systems. And so you can sometimes use these sort of everyday metaphors, but most mathematics, even when you use an everyday metaphor, it's at least as misleading as it is helpful. So the trouble is we don't have these simply visualizable metaphors for most mathematics.
Can you talk about applications of the mathematics, or is even that too abstract?
You can try it, but that's also for most of mathematics it's misleading too. One of the favourite ones a few years ago there was a thing called the Poincare conjecture that was solved by a Russian mathematician called Perelman, and it was an interesting news story for various reasons. But when people talked about the Poincare conjecture, they ended up talking about the difference between a coffee cup and a donut, and the difference between a ring donut and a jam donut. And as a mathematician who understands the Poincare conjecture, I knew what those metaphors meant. But from talking to people, and I give lots of popular talks, so I do talk to people, it was clear that when I was using that metaphor in a knowledgeable way, I was at least as likely to be misleading people as I was helping them. So I think even the simple metaphors only make sense to the people who really understand the mathematics and don't need them.
And this is one of the problems that I find very fascinating about mathematics, because if you're talking about the Poincare conjecture and Perelman, the one thing I can tell you about that story, correct me if I'm wrong, Perelman got a lot prize money because he solved an unsolvable problem, and he said, "I don't want your money." And
that's right.
That's what I know about the guy. But this is the thing about mathematicians. The New York Times, not too long ago, ran this great profile on Terence Tao, one of the greatest living mathematicians right now. But it's all about his life. And it's very little about the math, because the math is too hard.
Yeah.
So let's talk about how awesome the guy is. And this is
versus like scientists,
versus
you can
the
talk
actual
about their
math.
discoveries, and we talk about Darwin, we talk about evolution.
I couldn't tell you about the life stories of all the scientists who do these cool experiments, but I can tell you the life stories of some of the mathematicians, because that's all I can access. You know?
And that really is a news story. It's what I do on NPR. It's what I do in many cases. It's what mathematicians do. We talk about the people, because everyone likes stories. Human beings are storytellers. We understand the world in terms of stories, and so. When you've got something that's completely inaccessible, shift gear and talk about the mathematicians. And the mathematicians they're interesting intrinsically just because they're mathematicians, for one thing. They do this weird stuff that nobody else understands. So that already makes them a sort of an interesting case.
Mm-hmm.
Do you think this is a problem with journalists, or not a problem, but like this is an issue with math, where if only there were journalists that better understood math, we might actually get a better understanding of what's going on here? Or is that's not going to happen in the same way a great science writer can really elucidate what's going on?
The reason some people like myself, Ed Frenkel, one or two other people, Stephen Strogatz, you look at the people who are sort of science journalists on the radio and the magazines, the newspapers, we are professional mathematicians. So really what's happened is a small number of us that are in the business have stepped up to the plate and done the science journalism. Even when you look at these mathematicians like Erica Claridge and one or two others that are professional journalists, they have PhDs in mathematics. UC Santa Cruz many years ago started a journalism school to teach science journalism to people with PhDs, and a whole bunch of people came forward and sort of gave up the academic research career and became journalists. So the only people who write science journalism for mathematics now are either professionals like myself who do it on the side, or they're people who have been professional mathematicians who switched and became journalists. But without a PhD in mathematics, it's almost impossible to write good mathematics journalism, because you just don't have the internal understanding of the subject.
How do you approach a subject if you know certain branches of mathematics very well?
Yeah.
Can you tell us about a time when you tried to cover, a brand new branch of mathematics for you? What's your process of trying to figure out, how to explain it to people who know nothing about it?
Yeah. In fact, in 2000, when the Clear Mathematics Institute instituted the Millennium Problems, this was the year 2000. The Clear Mathematics Institute offered these prizes. They said they picked 7 of the most difficult unsolved problems of mathematics. They called them the Millennium Problems. Each one of them was given $1 million prize. The Poincare conjecture, by the way, was one of those problems. That was the first and only one so far to have been solved. But these prizes were announced in 2000 because I've got a track record as a science writer. Several publishers approached me and said, would I write a popular book on the Millennium Problems? And I said, look, I know book. 2 of the problems. Yeah, I understand 2 of them. I don't know anything about the other 5. And I said, it would take too long. Well, they twisted my arm. They flattered me. They did all the usual things, took me out to dinner. And eventually I said, OK, I'll write this book. And so then I was faced with the reality of having to learn 5 new branches of mathematics to explain these problems. And it did actually take me the best part of a year. It was great fun. And I had the benefit that I was able to talk to people who did understand it. So what I did was I got in touch with experts in those domains and was able to talk to them. And the fact is, if you're an expert in one branch of mathematics, it's not that difficult to get a good general sense of a different part of mathematics, a different branch of mathematics. You won't be able to work in it, but you will be able to follow what they do and understand it, because it's not that different. There's a lot of differences in the particulars, but the general approach to mathematics is such that if you've mastered one area of mathematics, you can actually get a pretty good understanding, in the sense of an understanding, not being able to do it, of a different branch of mathematics.
Can I ask another dumb question? I'm full of them tonight. When we say that there's unsolvable problems, what does that mean? I know that's such a stupid question.
We actually use 2 words. We talk about unsolved problems. An unsolved problem is a problem that's been raised and no one has yet solved it. An example would have been the twin, well, actually still unsolved. Let's go back to Fermat's last theorem. Fermat's last theorem, until 1994, that was one of the most famous unsolved problems of mathematics. After Andrew Wiles proved it, solved it, it's now a solved theorem. It's now a theorem.
And so that's the one that I can explain to my high school students, because I did.
So you can explain it to me.
And it's basically saying we all know the Pythagorean theorem, a squared plus b squared equals c squared.
Yeah.
Well, what if it wasn't squared? What if it was a bigger number? What if it's cubed? What if it's to the 4th or any number bigger than that? Right. Is there any solution to that?
Yeah. And then so that was an unsolved problem. That's now a solved problem. There's another class of problems that are called unsolvable problems. These are problems where mathematicians have been able to prove conclusively that problem cannot be solved. In fact, that's what I did my PhD on. The methods for doing that were developed in the 1960s, actually here at Stanford, by a deceased colleague of mine, Paul Cohen. He developed a branch of mathematics, a set of techniques that allowed you to go in and look at a problem that had been an unsolved problem and show that, in fact, it could not be solved. And what happened following his results was a whole group of us, maybe 100 mathematicians, got their PhDs by going through the literature, looking at problems that were unsolved and proving that they were unsolvable.
And is that really an advance? I mean, if you say, hey, we didn't know the answer to this, but now we know the answer is there's no solution. We can't figure this out. Is that actually helpful?
Oh, yeah, because it means you'd be completely wasting your time trying to solve it. A classic case would be squaring the circle. As a well-known mathematician, I get these papers sent to me fairly regularly about squaring the circle. And that's been known for hundreds of years that you cannot square the circle. Knowing that you cannot square the circle means that no professional mathematician would waste a moment of their time trying to prove that you could square the circle, because they know it's impossible. Now, amateurs don't understand the distinction between unsolved and unsolvable. So people keep literally wasting their time trying to solve problems which are known to be unsolvable.
So we can at least save time if we could say,
we can save time. It's a positive result. It actually, what it does is it says this particular question is beyond the power of mathematics. Mathematics cannot solve all the problems that look like mathematical problems. You know, I mean, what else is new? I mean, in most walks of life, people accept that you can't solve all the problems. You know, if we could, we'd have solved the problems in the Middle East a long time ago. They're getting worse. But, you know, but in that case, I guess people would be very pessimistic if they said it's unsolvable. What most people will say is we haven't figured out how to solve it yet.
Why do people take so much pride almost in saying, "Oh, I'm not good at math"? Like, "Oh, I'm sorry, I can't calculate the tip. That's too complicated for me. I was never good at math." They say that with a sort of like, "This is not a big deal." But they would never say,
"Oh, I don't really read."
But they don't say, "I don't." Oh, they might say, "I don't really read," but no one would ever say, "I'm illiterate. I can't read." Yeah, but they could say, "I can't do math." Whoops.
Yeah, well, that's probably because they don't realize that when someone says that to a mathematician, we think, "What a jerk. What a Philistine. What an ignorant person who doesn't even know that they are a Philistine." Because if there's a walk, you're a Philistine, if there's a part of human culture that you are proud not to be aware of, I would be horrified. I would never dream of saying it. I don't know anything about music or literature or whatever. I mean, and if I was ignorant, I would fake it, right? I mean, because I wouldn't want to be thought ignorant.
Yeah.
And so it's a bizarre attitude that people say there's this area of human thought that's been going for thousands of years. Some of the greatest minds have contributed to it. There's this whole body of literature, and I know nothing about it. Well, what you've said to me is you're a Philistine. And I don't always tell them that to their face, but that's
probably a good idea.
So tracing it back, like I remember my elementary school math classes, junior high math classes being like less than compelling. So what can we do to get kids and young adults more interested in math?
Oh, there's a couple of things. I mean, my own particular research over the last 10 years has been in developing video games to help people learn mathematics, because when you do mathematics in a video game, you're doing it in a different way. And almost, any of these, I mean, I played World of Warcraft for many years. World of Warcraft was out and out a mathematics game. It was about statistics, probability, optimization. It was using mathematical techniques all the time. It's just that the game was designed to sort of make it feel differently. And yet people who did well in World of Warcraft were solving math problems either singly or in groups. So that's one way you could go. The other way is, game learning is a growing field, but it's in a separate domain at the moment. The other way is just basing mathematical problems. With modern computers, the reason mathematical problems were these sort of silly things about trains leaving stations was people had to give problems that could be solved without any computational aid. You had to be able to solve it in 20 minutes using nothing more than a sort of a ruler and maybe a paper and pencil calculation and later a hand calculator. With modern computers, you carry around with your iPhone or whatever, so much computing power that there's no reason why you can't give people real problems that are interesting. Like what is the likelihood that the train you're traveling on is going to have a couple of terrorists on it? What's the likelihood that there'll be a terrorist and 3 American soldiers, etc., that can sort of protect us? So with modern techniques, you can find all of the data on the internet within a few minutes, and you can work the problem mathematically, and the computation would be too difficult to do by hand, but you can do it automatically. So simply by giving people problems that are relevant to them, traveling on a train is relevant if you're about to go to Europe and travel on a train, you'd be interested. If you're not, you could look at, the likelihood of an outcome of an election or a sporting event or anything whatsoever. Mathematics is everywhere. We can suck these problems out of the real world, use real world data, and still do the mathematics.
It is funny that I taught algebra, I taught trigonometry, a lot of things in between. And you would always get the when are we going to use this question. Yeah. But when I taught advanced placement statistics, that question never came up.
Yeah, but a kid who's in advanced placement statistics isn't going to ask a dick question like that.
Trust me, honors kids ask the dickiest questions. But it's because everything we did in statistics was a real question. And everyone saw where the application was. And that made it interesting. It was also interesting as a shift in when I was teaching, which is we were getting... I want to see less computation because we have the tools for that.
Right.
And I want you to write out an explanation. Like, what's your thought process for this?
Sure.
Explain this to a 5-year-old. That's a more interesting question to me than just solve this problem.
Well, I think an interesting question would be, so obviously we think basic addition, subtraction, multiplication is absolutely something everybody should be able to use. And on the other side of that, statistics or using a calculator properly is something that is useful. What about, like, should we still be teaching kids, like, long division, even though realistically they're not going to have to use long division? Like, they're going to have to use addition. They're going to have to use multiplication. They have to figure out tip percentages, 20%.
It's not that hard.
Yeah. No. The only rationale, I mean, at some point in an education, you ought to understand the notion of a multi-step algorithm because that's the basis of a lot of things in modern life. Mm-hmm. And the only rationale for using long division is it is a good example of a multi-step algorithm that in fact uses the place value system of arithmetic. So using it, teaching it as a way of understanding place value system and an algorithm makes sense. But you're not teaching it because people use it. You're actually not doing that with even the algorithms for multiplication. Because when we've got a number of more than a couple of digits, every one of us pulls out a calculator. Sure. Because it's just quicker and easier and more accurate. So even today, the multiplication algorithm is only taught, it's not taught to be used, it's taught to help people understand place value system and algorithms. And in fact, one of the things that the Common Core has been encouraging is the use not of the classical algorithms, but of algorithms that are much better at helping people understand arithmetic and place value systems. So when you see these posts on Facebook, the way they say, my kid has been taught this weird way of doing multiplication. No, that's not what's going on. The kid has really been taught about numbers, place value system and algorithms. And rather than do that with an algorithm that was optimized for computational efficiency in the 13th century, we're saying in the day of calculators today, use an algorithm that's better helps people understand place value system and algorithms. So it's no longer about learning a method to do multiplication. It's using multiplication to understand the number system.
I've said this before a couple times, but I've been writing about atheism for like 8 years. Yep. And by far the most popular thing I have ever written is saying exactly what you just said about Common Core. Like, Common Core math isn't the problem. It's you don't understand how math works.
I read that article that you wrote, and it completely made sense, because I saw that same dumb thing like, my kid's learning this stupid thing.
So when you hear politicians complaining about how Common Core is a bad thing, what is it that they don't get?
Everything,
besides everything all the
things.
time, yeah.
Well, yeah, I mean, there's many ways of answering that one. I think John Stewart would do a better job of that than I would do it. But
let me ask you slightly...
Okay, go on, yeah.
No, I'll ask you a slightly related question, which is the Khan Academy, something like that.
Yeah.
That
Wait,
is
what's that?
so helpful, like YouTube videos to teach you all these various subjects in school.
Oh.
One of the criticisms I've heard of Khan Academy is it kind of teaches you computation, rote mathematics. Is that really helpful for kids?
I think rote mathematics. You're not asking me.
I mean, what it does is it's a very good, freely available platform for teaching mathematics that was important in the 19th century and earlier, but in a sense is no longer important, with one important exception. It actually still is important for people to master a lot of procedures because of the standardized tests. So what Salman Khan does, and I know him personally, so I would like to think he's a friend of mine, although I do critique it, because what he's doing is he's filled a market niche. There is a big niche for people who want to pass exams. And he's developed a platform that is very good at helping people pass exams, but it's not helping them learn mathematics. It's not about making them mathematicians or mathematically able people. It's about helping them pass mathematics. That's valuable in today's society, but I hope we're going to soon get beyond the stage where mathematics is about passing these standardized tests, because they actually detract from learning mathematics. Mathematics today is about solving real-world problems that involve novel twists.
And that's actually getting more to the heart of what the Common Core standards are all about.
But there is
Common Core is actually mathematics for the 21st century.
But there is some value in learning things by rote, right? Like, you can't do the math when it's like 6 times 10 is... Like, you have to just know that off the top of your head. Like, so there is some value in learning, right? Am I completely off?
Yeah, some stuff certainly needs to. It's the same with everything else. You've got some stuff that needs to be mastered. However, most of us find that we master the basic stuff when we encounter it repeatedly in a meaningful situation. Learning it to be used tomorrow is not the best way, because people don't learn that way. People actually find they master things by repetition when they have to do that repetition in the course of doing something that interests them.
I have one
Yeah,
last
so yeah,
question.
absolutely, you need to master. Yeah, go ahead.
I have one last question for you, which is maybe just because people who are outside the mathematical world wouldn't know this, and I'm curious too. When professional mathematicians talk about various things that they're working on, maybe like you said, that other branches of math those people may not be working on, how do they communicate with each other? How do they collaborate when they're all doing so many different things?
Well, as I mentioned before, even though the specific branches of mathematics have their own arcane uses of language and very specialized, the basic thought processes are essentially the same. A mathematician is a mathematician is a mathematician. So it actually, within the space of half an hour, you can get a pretty good sense of what that person's working on. You may even be able to make a suggestion that helps them solve their problem because you're going to see it in a different way. So it's not as difficult as that to understand what each other's doing in general terms. If, however, I'm sitting next to a mathematician in a different domain who says, here's a proof I've just developed, I'd like you to check this proof for me, I would have to say, they would never ask me that because they would know that I wouldn't be able to do it. So in terms of checking the details, you can't do that. But in terms of, it's like an automobile. I can get into any car and drive it. But if I then have to lift the hood and do some tinkering, the only one I can do is my own car because I got used to it.
Yeah.
You can drive any other vehicle, but you can't sort of go and start fiddling with it and tuning it and tinkering with it.
Let me ask one revision of that same question, which is, how do they physically communicate? I mean, are they literally, let me sit you down and tell you what type of math I'm working on?
Over drinks.
Yeah, over drinks.
Drinks helps, yeah.
Or do they have are they communicating through their research papers or through blog posts like Terence Tao is doing in a lot of ways, though that's not maybe to other mathematicians per se?
In terms of sitting down and having drinks, mathematics is one of the quintessential napkin problem disciplines. You have to have a napkin. If mathematicians are talking together, sooner or later they're going to have to write on something. It may be, there's famous cases where they've scribbled things on stones, on bridges and things, but you have to have some surface, a blackboard, a whiteboard, a napkin, a piece of paper, the back of your hand or whatever. Sooner or later you have to draw symbols. And one of the reasons mathematicians can now collaborate over the internet is because all of the social networking tools now allow us to share diagrams and images and even to work together on a common workspace, because working together on a common visual workspace is an extremely powerful tool.
Well, thank you so much for helping us better understand this ridiculously complicated type of subject. We really appreciate it.
Absolutely, my pleasure.
Yeah, thank you so much. We'll have all the links in the show notes to some of the stuff we talked about. And hopefully people will check out how to do math.
Thanks for breaking it down for me, Keith. I feel like I learned so much.
My pleasure. Thanks again. Bye-bye.
Thanks for listening to the podcast for friendlyatheist.com. This episode was taped at Cinnamon Sound Studios in Aurora, Illinois, and the music was written and performed by Brad Chagdis. If you like what you're hearing, please consider making a contribution at patreon.com/Hemant, that's He-Man-T. We appreciate your support. I'm Hemant Mehta.
And I'm Jessica Blumke. We hope you'll join us next time.